today I'm going to talk a bit about my thesis work and the background around it. But I was thinking that first let's go through the basics. So how are magnetic fields produced? Well, magnetic fields are produced by the motion of charged particles. So, and at the same time, when you have a magnetic field, charged particle will feel a force of the magnetic field bending their trajectories. So whenever you have charged particles, you will very likely also have magnetic fields. So magnetic fields and charged particles go hand in hand. And two of the most well-known astrophysical magnetic fields come, of course, from our solar system. So first, we have the Earth's magnetic field, which is generated from the liquid outer core, which is filled with charged particles that move around. This creates the magnetic field. And then we have the sun. And the sun, of course, is just a ball of charged particle. It's a plasma, right? So it forms its magnetic field from its interior motions. And the sun's surface is very unstable. So it very frequently erupts and sends out a big burst of charged particles out into space. Some of these, of course, goes towards the Earth, but the Earth, luckily, we have a magnetic field. So the magnetic field deflects these charged particles, and some of them are deflected in the polar regions, which excites the atmosphere and creates the beautiful aurora, or northern lights. And this was exactly what Birkeland experimented with, right? So he set up, in his laboratory, he set up an experiment to simulate this sort of process. So he had a magnetic ball, or magnetized ball, which he shot rays of charged particle at, and looked at how are these deflected. And you can see here on the right picture that these, like the charged particle, when they hit the magnetic ball, they create this, basically, this light around the poles, which correlated very well with the aurora. So this is a very smart way to explain the aurora during his time. But now let's zoom out. So now let's look at the present day, because it turns out that galaxies are also magnetized, because most gas in galaxies actually contain large fraction of charged particle. And here to the right, we can see actually a picture from the Planck satellite, looking at basically the synchrotron radiation, which depicts the strength of the magnetic field. So we can see that magnetic field is very strong in the center, but that it flares out into the also circumgalactic medium. And here on the left, we can see the Whirlpool galaxy, which is taken with the Hubble telescope. And here it's a bit hard to see, but you can see the lines which shows the direction of the magnetic field. But it is basically along the spiral arms of the galaxy. And very surprisingly is that these magnetic fields are very strong compared to what we maybe initially thought. Because if we make calculations of processes that can create the primordial fields very early on in the galaxies, we get a number of something like 10 to the minus 20 Gauss. But magnetic fields in galaxies is about 10 to the minus 6, or even higher in some very starbursty galaxies. So the magnetic field must have grown 10 to the 14 times stronger during the evolution of the universe. So this requires a fast growth of magnetic fields. So what kind of process can explain this? Well, dynamo. So dynamo theory is a way the magnetic field can grow exponentially fast. And dynamo only, in a sense, means that you're transferring kinetic energy to the magnetic energy. And basically, an exponential, like a fast dynamo, an example of a fast dynamo is I like to show this toy diagram, because what you do is basically you take a magnetic loop, you stretch it, you twist it, and you fold it. And then you get basically 2 times the magnetic field. And this is done by the underlying fluid motions. So what kind of fluid motions can do this sort of thing? Well, turbulence, of course. And I think this is very nicely depicted in this bottom picture. So we begin with just a vertical magnetic field. And then in this box, we have a turbulent field, which is basically twisting and tangling up the magnetic field, stretching it, twisting it, and folding it, which means that we have an increase in the magnetic fields. And we also saw, right, this ordered magnetic field in our galaxy. And for that, the rotation in the galaxy can actually help. Now, what is the role of magnetic field? Okay, so we have strong magnetic fields in the galaxies, but what does this mean? Well, the thing is that if we look at the energy content of the magnetic field and compare it to, for example, the thermal energy content, they are about the same, or even in some cases, the magnetic field seems to be even stronger. This means that they are very dynamically important. And this, I think, a good example of this is, for example, if you look at the collapse of molecular clouds. So the collapse of molecular clouds is the first stage of the star formation process, because this is what creates the stellar nurseries. And if you have a strong magnetic field, this will basically hinder the collapse or slow down the collapse, resulting in less star formation. And this has a big effect when you do numerical modeling of the galaxy, of course. Second, it is also very important when it comes to cosmic rays. As Gunnar showed, he had an instrument where he had 2 magnets and cosmic rays coming in, right, and bending them. And so cosmic rays are released in supernova explosions. And these are highly energetic particles moving near the speed of light. And they will basically get trapped by the galactic magnetic field, and it is believed that they can potentially drive galactic outflows. Another role in magnetic fields is that we have found them around the accretion disks of black hole. And in theory, it is believed that the magnetic field, because of basically instability, increases the transport of material towards the black hole, making them brighter than what we would expect. And also magnetic fields is believed to be an essential component in the formation of astrophysical jets. Yes, so the goals of my thesis work was to basically develop a numerical model for galaxy simulation that can properly model magnetic fields, and apply this to methods that are, or processes that are very, very challenging. One case is the jet formation of the magnetized core collapse, and to capture the periodic magnetic field reversals present in accretion disks. And of course, explore the dynamo processes. And so what we want to do is basically create a virtual laboratory. Just like Birkeland, right? He set up his system. We do so too, but we do it using computers and big. So here is me sending commands to a big supercomputer cluster in Europe and letting it do the work, in a sense. Yes, but as was said, magnetic fields are very hard to properly model numerically. And this is why, actually, like we have done galaxy simulations for quite a while, right? But magnetic fields have never been added because they go unstable. They break down. So it's very hard. And I think 2 examples that show this very nicely is, for example, the magnetized cloud collapse, where you expect at the end of collapse to have the formation of a jet. However, you can see in the old model, there's no jet, right, in the left picture here. And another case is in accretion disks. So if we look at the side-on magnetic field in an accretion disk, we actually expect it to have magnetic field reversal. So the magnetic field goes from positive, negative, positive as time goes on. But when we simulate it with older models, we just get this, which is sort of a runaway growth of the magnetic field, so it goes unstable, basically. But now, with the new numerical model that I developed during my PhD, we can see that we can successfully capture jet formation, and we can see that we do capture the periodic magnetic field reversals in the accretion disks for a very long time. And this is the first particle method to ever do this in 3 dimensions. And I thought it would be interesting to actually just explain the magnetic structure around a jet. So here we can see a 3D render of a jet being formed. And here we can see the magnetic field lines, how they look at different radius, in a sense. So along the jet, we can see that the magnetic field basically points straight up along the jet. But then as we go further out, we can see the magnetic field basically coils around this jet. So basically like a coil gun, shooting it up, accelerating it up. And then we come to the galaxy simulations that we do. So here we have an isolated Milky Way type galaxies. We set up some initial field, and then we let it run. And we can see how it develops. So first, it's quite a weak field, but as it turns more red, it grows in strength. And you can see that the growth basically starts happening in the spiral arm structure. That's where you have large modes of turbulence being generated. And we ran 60 galaxy simulations with a lot of different varying setups because we wanted to test all kinds of different parameters. And what we find is, in many cases, the magnetic field amplifies very quickly, reaching saturation in about 1.2 gigayears. And this is in the paper, in the article, if you're interested, you can read a bit more. And we show that the dynamo processes are captured. And we see a very strong mean field dynamo, which is consistent to the classical theory of an alpha omega dynamo. And we can also see that during this movie, right, that the magnetic field was pushed out of the galaxy, basically magnetizing the whole circumgalactic medium. And this further, we also have started to look at comparing this, also our simulations with observations now. So here is some observation that you can see. So this is observation of with the radio telescopes, where they can basically, from the polarization, check the direction of the field. And you can see here is a side-on view of the galaxies, and the arrows go up, down, up, down, up, down. And then in our simulation, here, the blue is down, the red is up. So you have up, down, up, down, up, down. So a very similar pattern. So this work has increased our understanding of galaxies, because this is still very early, right? As I said, we have just recently started to add magnetic fields to galaxies. So this is first step, and thank you very much.